All right, good morning. So, as I said earlier, we're going to continue, building mathematical models of certain problems. And today we're going to continue with several other examples, just to illustrate how one can model a given problem as a mathematical model, as an optimization model. And in particular, of course, we're going to be focusing on problems that can be modeled as an LP problem, right? As a linear programming problem. So if you recall from last time, there are certain assumptions that should be satisfied by a problem so that we can model it as an LP problem. And so in the next few weeks, including this one, we can actually look at problems or some types of problems that can be modeled as an LP problem, okay? So this is example number 5, and here's the statement of the problem. So suppose that an oil refinery distills crude oil from Saudi Arabia and Venezuela into gasoline, jet fuel, and lubricants. So I'm going to give you some information about the problem now. So So if the refinery actually distills 1 ton of Saudi Arabia crude oil, then it results in the following products. So we have gasoline, jet fuel, and lubricants. So we get 0.3 tons, 0.4 tons here, and 0.2 tons. So if the refinery actually distills 1 ton of Saudi Arabia crude oil, then these are the resulting products and the corresponding proportions, basically. On the other hand, if the refinery uses Venezuela oil, then here are the outputs. So you get 0.4 tons of gasoline, 0.2 tons of jet fuel, and 0.3 tons of lubricants. Well, so 1 ton of oil actually enters the system, and if you actually add up these numbers, only 0.9 tons of product comes out of the system. So what happens to the remaining one? Well, the remaining one, we assume that it gets lost in refining. So the remaining 0.1 tons is lost in refining. So for one reason or another, okay? So as a result, 1 ton of oil actually enters the system, but a total of 0.9 tons of product comes out of the system. Then we have the following cost table. So the cost is given in terms of dollars per ton. So for Saudi Arabia oil, the cost per ton is $600. And for Venezuela oil, it's $550. So these are the purchasing prices. So our refinery actually buys oil in tons, and these are the sales prices per ton. Another information is the following. So at most 90 tons can be purchased from Saudi Arabia. And we also assume that at most 60 tons can be purchased from Venezuela. So these numbers are daily numbers. So in a given day, you can purchase at most 90 tons from Saudi Arabia and at most 60 tons from Venezuela. What else? So we also have the demand information. So the daily demand is 20 tons of gasoline, 15 tons of jet fuel, and finally 5 tons of lubricants. So this is the demand that the refinery has to meet on a daily basis. Okay. So we assume that demand is fixed, so every day we have to actually meet this demand. And the question is the following. So how should the demand be met? At a minimum total cost. So let me just go over the problem once again. So suppose that there's an oil refinery, okay? And what they do is they purchase crude oil and they distill it, okay? And they have 3 different products. They produce gasoline, jet fuel, and lubricants. And since we assume that the oil might be of different quality from Saudi Arabia and Venezuela, they actually yield different proportions of products, okay, which is given in the first table. And during this process, we lose 0.1 tons. Okay, so as I mentioned, actually 1 ton of oil comes into the system, but only 0.9 tons of products come out of our system. The purchasing prices are given over there. So the price per ton for Saudi Arabia oil is $600, and the price per ton of Venezuela oil is $550. Okay. So there are some limitations from these countries, let's say, on exports, for instance. So we can purchase at most 90 tons per day from Saudi Arabia and at most 60 tons per day from Venezuela. So we have to produce 20 tons of gasoline, 15 tons of jet fuel, and 5 tons of lubricants every day. So this is demand that we have to meet. And the question is, how can we meet this demand at a minimum total cost? So how should I actually sort of achieve this demand at a minimum total cost? Okay? Is the problem clear, first of all? All right. So let's start with our decision variables then. Now, in this problem, what are the factors that we can control? So what can we control in this problem? What are our decision variables? Exactly. So in this problem, there are 2 things actually we can control. How much oil we're going to purchase from Saudi Arabia and how much oil we're going to purchase from Venezuela on a daily basis, right? So as a result, I'm going to define 2 variables. I'm going to call them x1 and x2. So x1 is the number of tons of oil purchased daily from Saudi Arabia. Okay? And the second one is similarly, it's going to be a number of tons of oil, well, actually crude oil to be more precise, purchased daily from Venezuela. Okay? Now, do my decision variables satisfy the assumption of divisibility? So can they take fractional values? Yes, they can, right? Because we're talking about the number of tons of oil, so as a result, the divisibility assumption is satisfied, so we're good, right? So we can still live in the framework of linear programming. All right, so any other decision variables we need for this problem? Well, not really, right? Because everything else is already given to us, right? So these are beyond our control, so these are the parameters of the problem. And in this problem, there's nothing else we can control. So we cannot really control the sales price. We cannot control, these outcomes. We cannot control these numbers and so on and so forth. So as a result, the only things we can control are how much oil we're going to purchase from each of the 2 countries, basically, right? Okay. All right, so let's try to set up our model. So what is our objective? So we want to minimize total cost, right? Okay. So what's the source of the cost? Well, the source is basically sales prices, right? Okay, or purchasing prices, more precisely. So I should minimize my total cost. So how can I express my total cost in terms of my decision variables? So since I'm trying to minimize this is going to be a minimization problem, right? So first of all, I'm going to start with the word min. So now I need to express my total cost in terms of my decision variables, okay? So the cost is given in terms of tons, and if I produce x1 tons of oil, sorry, if I purchase rather x1 tons of oil from Saudi Arabia, then I need to multiply by 600 to compute the corresponding cost, right? The purchasing price. So as a result, I'm going to have 600 x1 plus 550 x2. Now, does this look like a sort of valid LP objective function? Yes, it does, because you can think of this as C1 times x1 plus C2 times x2, right? So everything's okay so far. All right, what are the constraints? So there are several limitations, basically, right? So the first one is, for example, we cannot purchase an infinite amount, right? So there are limitations on x1, x2, basically. And there's a second sort of set of constraints, which is we have to meet the demand. So we cannot actually, purchase an arbitrary amount. We have to make sure that we produce, these amounts on a daily basis, okay? All right, so let me start with the easy ones first. How can I formulate these two conditions, these two constraints? Exactly. So x1 cannot be more than 90, right? So what does this relation say? Well, the number of tons of oil I purchase from Saudi Arabia cannot exceed 90. Okay? And indeed, that's the condition that I have to fulfill. And similarly, x2 cannot exceed 60. Right? So the number of tons of oil purchased from Venezuela cannot be more than 60. Okay? So those are the limitations that I cannot break in some sense. Okay? Any questions so far? So are these valid LP constraints? Yes, they are. So once again, I have 1 times x1 plus 0 times x2 here. And 0 times x1 plus 1 times x2, I have less than or equal to, which is okay, and another constant on the right-hand side. Okay, so everything is okay so far. So the question is the following. Now, how can I formulate the demand constraints? Well, let's think about it in the following way. So I can produce gasoline either from Saudi Arabia oil or from Venezuela oil, right? So what am I interested in? I'm interested in the total amount of gasoline I'm going to produce, okay? And I want to make sure that that amount should be 20, basically, right? Okay? Exactly. So since I can basically process every ton of oil I purchase, okay? If I purchase x1 tons of oil and if I process them, then I'm going to get 0.3 times x1 tons of gasoline, okay? And the same is true for x2. So if I purchase x2 tons of oil from Venezuela, and if I process it, then that's going to give me 0.4 times x2, okay? So what's the total gasoline I'm going to have? Well, I need to just add them up. So if I do that, I have 0.3 x1 plus 0.4 x2. So the right-hand side is 20. Okay? So what is the correct relationship I should have here? Let me leave it for now. Okay? I'm going to come back to that in a minute. So let me write down the similar constraint for jet fuel. So 0.4 x1 plus 0.2 x2. Again, I'm going to fill in the blank here. The right-hand side is 15. And finally, for lubricants, I have 0.2 x1 plus 0.3 x2. I have some relation. And the right-hand side is 5. Okay? So do we have any other restrictions on x1 and x2? They should be non-negative, right? So as a result, x1 should be non-negative because it corresponds to number of tons of oil we purchase, and x2 should be non-negative. So I'm almost done with my model. The only problem is I have to figure out the correct relationship in terms of these question marks, okay? Now let's think about this a little bit. So my goal is to meet the demand, right? So as a result, if I produce 20 tons of gasoline, 15 tons of jet fuel, and 5 tons of lubricants, then I'm done, okay? So ideally, what I can do is I can try to put equality constraints here, right? So I can make sure that this should be equal to 20, this should be equal to 15, and this should be equal to 5. Okay? However, there's a problem with that. Okay, does anybody see what the problem is? Well, see, the problem is the following. So if you look at the proportions, okay, it might not be possible for me to achieve these numbers exactly. Okay? Let me repeat it again. So there may never be a solution of x1 and x2 such that I get exactly 20 tons of gasoline, 15 tons of jet fuel, and 5 tons of lubricants. So in other words, here's another way to think about it. So if you put equality constraints here, okay, you have 2 unknowns, and you have 3 equations, right? And that may never have a solution. Okay? This is why linear algebra is a prerequisite for this course. Okay? All right, so now what else should I put? Well, so I need to make sure that I'm going to meet the demand, okay? But in order for me to meet the demand, I may have to produce more than I need. Does everybody see that? Okay, so what's the correct relationship then in terms of question marks here? Greater than or equal to, exactly. So that's going to be the correct relationship. So I'm going to allow myself to exceed the daily demand, okay? Because if I put equality constraints, I may never be able to satisfy demands exactly. Okay? So as a result, if I put greater or equal to constraints, then I'm going to make sure that I'm going to produce at least as much as the daily demands. And I can always find values of x1 and x2 that satisfy all of these relations. Okay? Does everybody see that? So this is important. Okay? As I said, if you put in equality constraints, then you may never satisfy demands exactly. Okay? But if you put greater or equal to constraints, since you're trying to minimize this, you may do some extra production. You may produce more than you need. But since you're trying to minimize total cost, you're not going to produce much more than you need in some sense. Okay? So in other words, since you cannot control these proportions, you have to make sure that you put these sort of greater or equal to constraints to meet the demand. Okay? Any questions? So that's important. All right. So does every constraint look in the form of an LP constraint? Yes, so every constraint, if you look at the left-hand side, I have C1 times x1 plus C2 times x2, and the right-hand side is a constant. And in between, I have either less than or equal to, or I have greater or equal to. Okay, so everything works out fine. So as a result, this would be an example of an LP problem. Okay? So in other words, this problem can be formulated as an LP problem in this way. Okay? As I mentioned, for now, we're going to just sort of stop here. We're not going to solve this model for now. But we're only interested in building this model, constructing this model. Okay? Any questions? All right. So let me continue with the next problem then. So this is example 6. So this is a typical problem known as transportation problem. Okay, so suppose that there are 2 power plants. There are 2 power plants that generate electricity . And there are 3 factories . There are 3 factories that use electricity in their production. So here's a typical picture that's easy to understand. So suppose that I have power plant 1 and power plant 2 here. Then I have three factories, which I'm going to call F1, F2, and F3. So I can send electricity from power plant 1 to factory 1, or factory 2, or factory 3, and similarly from power plant 2 to factory 1, 2, and 3. Okay? So this is where I produce electricity, and this is where I use electricity, basically. Okay? So I have the following information. So here are the capacities of these power plants. So suppose that the first one is 1,000 megawatts, and the second one has a capacity of 2,200 megawatts. So think of this as a daily capacity, for instance. Okay? And then we have the following demand. So factory 1 needs 1,500 megawatts per day. Factory 2 needs 750 megawatts per day. And finally, factory 3 also needs 750 megawatts per day. Okay? All right, so we again have the following cost information. So here are the transmission costs. And these are given in terms of, Turkish liras per megawatts. So I have the following matrix. I have my power plants here. I have my factories here. And numbers are 50, 100, and 60. And then 30, 20, and 35. Okay, so this is my cost information. So in other words, in order to send 1 megawatt of electricity from power point 1 to factory 1, I need to pay 50 liras. Okay? And the same is true for all other combinations. And the question is the following. So how do we satisfy total demand? At a minimum total cost. Okay? So once again, let me just explain the problem briefly. So we have two power plants that I call PP1 and PP2, which has respective capacities of 1,000 and 2,200. You can think of this as daily capacity or monthly capacity, if you like. Okay? And then we have three factories nearby, okay, which use electricity in their production. And we have the demands of factories, which is given on the right-hand side. We can send electricity from each power plant to each factory, but there's a certain cost. So you can think of the cost based on the distance, for instance. Okay? For example, it cost me 50 liras to send 1 megawatt of electricity from power point 1 to factory 1. And we have all the information over there. So the question is the following. So how do we satisfy total demand at a minimum total cost? So how can we satisfy demand of all three factories so that my total cost, my total transmission cost, of course, will be as small as possible? Okay? Is the problem clear, first of all? It's not clear? It's clear, okay. So the reason why this is called transportation problem is the following. You can think of these as your sources, okay? And these are your destinations, okay? So what you want to do is you want to send products from your sources to your destinations. So these are supply points, these are demand points, basically. And you want to sort of send products so that the total cost will be as small as possible, okay? So you can think of these as distribution centers, for instance. And you can think of these as clients or supermarkets and whatever. Okay, so this is a generic class of problems called transportation problem because you want to transport your goods from supply centers to demand points. Okay? Any questions about the problem? All right, so let's start modeling this problem now. Again, I'm going to start with the following. So what are my decision variables? So what are my decision variables? So in other words, what are the factors I can control? Well, so if you think about this a little bit, for each arrow that you see here, for each arc basically, I need to decide how much this electricity I'm going to send on this arc. Okay? So how many arcs are there? 6. So how many decision variables do I have? 6. So what I can do is the following. I can name them x1, x2, x3, x4, x5, x6. That would be okay. However, typically we do the following. So we can use actually 2 indices. Okay? We call it xij. This is for simplicity basically. You can label your decision variables whatever you like, and you can use as many indices or as many subscripts as you like. So xij can be thought of as the following. So it's number of megawatts of electricity transmitted from power plant I to factory J. So what are the possible values of I? 1, 2, right? Because there are 2 power plants. What are the possible values for J? 1, 2, 3. So basically you have to write that down. So I can take the value of 1 and 2, and J can take the value of 1, 2, and 3. So how many decision variables do I have? 6 basically, right? Because for I have 2 choices, for J I have 3 choices, and if you multiply them, you get 6 different variables, which correspond to 6 different arcs in this picture. Okay? x11 is how much electricity I'm going to send from power plant 1 to factory 1. x23 is how much electricity I'm going to send from power plant 2 to factory 3, for instance. Is notation clear? All right, so now what is my objective function? So I want to minimize total transmission cost, right? Okay. So what I need to do is I need to express my total transmission cost in terms of my decision variables. Okay. So how am I going to do that? Well, first of all, it's a minimization problem because we're minimizing total cost. Okay. So we start with the word min. So now I need to express my total transmission cost. Okay. So please pay attention to units. Basically, these are given in terms of liras per megawatts. And my decision variables are given in terms of number of megawatts, so I can multiply them. Okay. So if I do that, I'm going to have 50 times x11. Okay. Well, we can, for example, go row by row. So what's the second one? 100 times x12, right? So I'm sending from power plant 1 to factory 2. Then 60 times x13. So now I'm going to move on to the second row. So I'm going to have 30 times x21 this time, right? So I'm going to have 30 times x21 plus 20 times x22. And finally, 35 times x23. So basically, this is the expression we have. If you give me the values of x11 through x23, I can actually compute the total cost in terms of this function, basically, right? So I just plug in those values, and I obtain the total cost. Is this a valid objective function for LP? Yes. So once again, I have C1 times the first variable, C2 times the second variable, and so on and so forth. Okay? So this is a sort of valid form of objective function. Now let's figure out the constraints. So do we have any constraints? So we have capacity restrictions and we also have demand constraints, right? Okay, so let's start with the capacity constraints. Note that I cannot send more electricity than I can produce, right? From power plant 1. Okay, power plant 1. So from power plant 1, how much electricity do I send? Well, I send electricity to factory 1, factory 2, and factory 3. Okay, so what am I going to do? I'm going to add up x11 plus x12 plus x13. Okay. So there's going to be total electricity, total amount of electricity that I'm going to send from power plant 1. So let's write it down. I have x11 plus x12 plus x13. So once again, this is the total electricity, total amount of electricity I'm going to send from power plant 1. Okay? So what kind of a restriction should I have on this expression? Exactly. So I need to make sure that the total amount of electricity I'm going to send from power plant 1 cannot exceed its capacity. Okay? And the capacity of power plant 1 is 1,000. So as a result, this is going to be less than or equal to 1,000. Okay? So once again, this is a constraint in the form of an LP problem, right? So C1, 1 times x11 plus 1 times x12 plus 1 times x13 plus 0 times x21 plus 0 times and so on and so forth. Okay? I should do the same thing for the second power plant. So what's the corresponding constraint? So the amount of X I send from power plant 2 to factory 1 plus power plant 2 to factory 2 plus power plant 2 to factory 3 cannot be more than 2,200. Okay? So basically these are the capacity constraints, right? So these two constraints tell me that I cannot exceed the capacity of my power plants. Okay? What else do we have? Well, we also need to make sure that we meet the demands. Okay? So let me start with the first factory, factory 1. So factory 1 can sort of receive its electricity either from power plant 1 or power plant 2. Okay? All right, so what is the corresponding constraint? x11 plus x21 this time, right? So now I'm actually fixing the second one constant. So G is equal to 1. And I'm changing I from 1 to 2. Okay? In the first examples, the first index was constant. Okay? And we sum over the second index. And so is in this one. So when I write down the demand constraints, now I'm going to fix the second index. Okay? So I'm going to fix J to be 1, for instance, for factory 1. And I'm going to change the first index. Okay? So as a result, I have x11. This is the amount of electricity I'm going to send from power plant 1 to factory 1. Plus, there's this arc as well, right? So I can also send electricity from here. So what's the corresponding variable? x21, right? So plus x21. So what kind of a condition should that this expression satisfy? So right-hand side is 1,500. So in this case, it doesn't really matter, actually. Unlike the previous problem, you can either have equality or greater than or equal to constraints. Okay? So we can basically just say greater than or equal to, but in any optimal solution, you will never send more electricity than you need. Okay? Why not? Because, well, if you reduce the electricity that you send, then your cost will actually get smaller, right? So as a result, in the optimal solution, this will always be satisfied with equality. Okay? But there's no harm in writing it this way either. Okay? So you can always sort of write it in this way. So there's a difference in terms of these constraints between this problem and the last one. In the last one, we had to put greater than or equal to constraints. In this one, you can either put greater than or equal to or equality constraints. Both are fine. Okay? So that's the demand of first factory. For the second one, we have x12 plus x22. And the right-hand side should be 750. Okay? All right, so finally, I have to write the demand for factory 3. So how do I express the demand of factory 3? x13 plus x23. And this should be at least as large as 750. Okay? Is there a question? Question? All right. Do I need anything else? So we also have non-negativity constraints as usual, right? So, and one way of writing this is as follows. So you can simply say xij is greater than or equal to 0. And this is true for every value of I and every value of j. So basically, you can think of this as 6 constraints. Okay, so x11 is non-negative, x12 is non-negative, x13 is non-negative, and so on and so forth. So we have our total cost, we have the capacity restrictions, we have the demand restrictions, and we have non-negativity constraints. And if I can solve this problem, then I'm going to get an optimal solution of this problem, basically. Okay? It it's always a good idea to make sure that your constraints are in the form of an LP problem. And if you look at all the constraints, they're indeed in the form of an LP problem, right? So if you look at the left-hand side, you always have a constant times variable plus constant times another variable and so on and so forth. In the right-hand side, you have just constants. And in between, you have either less than or equal to or greater than equal to or equality constraints, okay? Any questions about the problem or the model? So one thing you should keep in mind is the following. So, despite the fact that linear programming has pretty strong assumptions, right? So they should be satisfied. And last time we argued that not every problem actually satisfies those assumptions, okay? So I just showed you two examples in which all those assumptions are satisfied, okay? So as a result, linear programming is not quite artificial in some sense, okay? It still has a lot of applications, and these are just two examples that can be modeled as an LP problem, okay? Any questions again? All right, so I'm going to continue with some other problem. So this is example 7. And this type of problems are called blending problems. So suppose that there's a company called OJ Inc. Okay, and they produce orange juice, let's say from 3 different grades of oranges. So oranges are graded 1. And 1 stands for poor. 2 stands for medium. And 3 stands for good, depending on the quality. So there's a company that produces orange juice, and it does this using different sort of types of oranges. And we assume that there are 3 types of oranges. So namely, we call them poor, medium, and good. Okay? So the company actually uses them in their production. And we have the following information. So for each grade of orange, we have the corresponding amount of juice that comes out of it. So for grade 1, we get actually 0.4 liters per kilogram. For grade 2, we get 0.5. And for grade 3, we get 0.6. So this basically means that for each kilogram of grade 1 orange, we actually obtain 0.4 liters of orange juice. For each kilogram of grade 2 orange, we get 0.5 liters of orange juice, and so on and so forth. Okay? Then we have the current stack. So these are given in terms of kilograms. So here are the grades, and these are the current stacks. So in the stack right now, we have 100 kilograms of grade 1 orange. We have 150 kilograms of grade 2 oranges, and we have 200 kilograms of grade 3 oranges. So these are the current inventory levels, so to speak, okay? Now, the company produces 3 different types of orange juice. Oranges from these oranges. And they call it superior, premium, and regular. Okay? So there are three different types of ingredients, and there are also three different types of products, final products. Okay? So we call them superior, premium, and regular orange juice. So we assume for now that demand is unlimited. So whatever you produce, you can sell. Okay? All right, so now I'm going to continue. All right, so what else do we have? We have the following production requirements. So since we have three different products, there should be something that distinguishes them from one another. So here are the production requirements. So here's the type of orange juice, and here is the minimum average grade. So for superior, the minimum average grade should be at least 2.4. For premium, the minimum average grade is 2.2. And for regular, the minimum average grade is 2.0. Now what does that mean? Well, remember, so we had different grades of oranges. Okay, so what we're going to do is we're going to actually mix them to actually produce our final products, which is superior, premium, or regular. But minimum average grade essentially means the following. When you produce superior orange juice, okay, you have to use better oranges, basically, okay, higher grade oranges, okay? And when you produce regular, for example, then you can use lower grade oranges as well, okay? So, however, you have to satisfy those minimum grade requirements. And I'm going to talk about that in a minute, basically, how we compute that. So for instance, if I use 1 kilogram of grade 1 and 1 kilogram of grade 3, okay, then what's the average grade? It's going to be 2, basically, right? Well, if I use 1 kilogram of grade 1 and 2 kilograms of grade 3, well, then you have to be careful a little bit, but it's not too hard to see that it's going to be a weighted average then. Okay, it's not going to be a straightforward average, but I'm going to multiply 1 by the kilograms, number of kilograms, and I'm going to multiply 3 by the number of kilograms. Then I'm going to divide it by the number of total kilograms, basically. Okay, so that's how I'm going to compute that. What else do we have? So we have the profit per liter. So for superior, we have 1.5. For premium, we have 1. And for regular, we have 0.75. So this is how much profit I have per liter of different types of orange juice. Then we also have the following requirements. So minimum daily production. So for superior, we have to produce at least 45 liters per day. For premium, we have to produce at least 60 per day. And for regular, we have to produce 100 per day. So these are the minimum daily production levels that we should achieve. So these are in terms of liters. So the question is the following: how to maximize total profit while meeting production requirements, meeting all production requirements. So this is a longer problem, so let me just go over the problem once more. So essentially, you can think of this similarly to the transportation problem. So there are three types of oranges. Okay? So this is grade 1, grade 2, and grade 3. Okay? And then there are three types of orange juices that we produce with these oranges. And I call them superior, premium, and regular. Now I'm going to produce these orange juices from the oranges. Okay? So for example, for superior, I can use some grade 1 oranges, some grade 2 oranges, and some grade 3 oranges. For premium, I can use some grade 1, grade 2, and grade 3. And similarly for regular, I can use some grade 1, grade 2, and grade 3. Now in doing so, I cannot be completely arbitrary. I cannot really do what I want, but I have to obey certain restrictions. Okay? What are the restrictions? So for example, I'm limited with the stock. Okay? So the amount of oranges is not unlimited. Okay? There are certain production requirements that I need to fulfill. So I need to make sure that, for example, when I produce superior, I should use more of the higher grade oranges. Okay? Then I also have to make sure that every day I have to produce at least 45 liters of superior, 60 liters of premium, and 100 liters of regular. Okay? So I need to fulfill all of these restrictions. And then here's my profit information. Okay? So the question is, how can I maximize my total profit while satisfying all the requirements in the problem? Okay? Is the problem clear? So is it clear why it's called a blending problem? Well, blending basically means mixing. Okay? So essentially what we're doing is we're mixing these three grades of oranges to produce different products, basically. Okay? And the question essentially is, what's the proportion in which I need to blend these oranges, okay, to obtain my final products? So as I mentioned earlier, similar to transportation problem, this is a typical problem as well. For example, you can also apply this to other settings. So, if you buy gas for your car, for instance, so they have different products, right? So 97, 95, and so on and so forth. So those are similar to these type of grades, okay? So they also mix actually gasoline. And when they do so, when you buy a higher grade oil, you get actually products which are composed of better ingredients in some sense. Okay? So, instead of 2.4, you have 97, 95, 93, and so on and so forth. So that's essentially pretty much the same sort of rating they use. Okay? So as a result, this type of problems actually comes up everywhere. So in sort of, production of orange juices, production of gasoline, and so on and so forth.